Hello everyone and welcome to Electrical Engineering and LTspice tutorials. In this tutorial we explain how to simulate an active low-pass filter in LTspice. Over here you can see the basic structure of a low-pass filter. Here you can see an ideal op-amp, and in these two feedback loops you can see a resistor and capacitor. Then you can see this resistor going to the inverting input, and over here V3 is the input voltage. Here, for simulation purposes, we apply an input sinusoidal signal. Then we measure the output over here at this output node. The graph shown over here shows the input and output. Namely, the blue sinusoidal signal, that is this signal, shows the input. This is a sinusoidal signal whose amplitude is 1. On the other hand, this green sinusoidal that is shifted and attenuated represents the output. That is, the green represents the voltage measured at this point, and the blue represents the voltage measured at this point. As you can see, the output signal is attenuated and shifted for 180 degrees approximately with respect to the input signal. In this video tutorial, we explain how to simulate this circuit from scratch, and furthermore, we explain how to validate this simulation by using the basic theoretical results of low-pass filters. So let's immediately start. Before we start with simulations, let's briefly revise the basic theory of active low-pass filters. The theoretical results will help us to validate LTspice simulation results. Here's our filter once again. Vi is the input voltage and Vo is the output voltage. In our previous tutorial that can be found on our YouTube channel, we derived this transfer function of this circuit. Namely, over here, V O of S is the Laplace transform of the output voltage and Vi of S is the Laplace transform of the input voltage. And the transfer function has this form. Observe several things over here. First of all, this is indeed a low-pass filter because of this term in the denominator. Note that we have a negative amplification, which will introduce a phase shift, and you can see that R2 and R1 resistors can be actually chosen to tune the amplification or attenuation of this circuit. From this equation, we can obtain the magnitude response, that is, we can obtain the frequency response, which is obviously given by this equation. From this equation, we can clearly identify the break frequency. Namely, the break frequency is the frequency omega for which the magnitude response is equal to 1 over square root of 2. That is, break frequency is the frequency for which the magnitude response is approximately 0.707. This number 0.707 means that the output signal amplitude will be equal to 0.707 multiplying the input signal amplitude. That is, the input signals will be attenuated 0.707 compared to output signals. That is, the output signals will be attenuated with respect to the input signals, and the attenuation factor is 0.707. If we now substitute this equation over here, we can find omega. And obviously omega b is 1 over R2c, and if we transform this to hertz, we will obtain that the break frequency is 1 over 2 pi R2c. This theoretical result will enable us to validate the LTspice simulation results. Namely, we will do the following. We will put an input signal that will have the frequency that is exactly the break frequency in hertz, and we are expecting that the amplitude of the output signal will be 0.707 multiplying the amplitude of the input signal. And if that's the case, this means that the LTspice simulation is correctly performed. So let's start with LTspice simulation. Okay, let's start. Once you open LTspice, you will see this empty screen, then click on File and click on New Schematics. And let's start adding the elements or the components. First of all, let's add our ideal op-amp. Click over here, then double click on op-amps, then move the slider all the way right and click on Universal Op-Amp 1. This is a linear single-pole op-amp with no internal nodes or output voltage range limits. And let's place it over here. Good. Next, let's provide power to this op-amp. Click on this voltage source and place one voltage source here, another voltage source over here, and then do the right click. Good. Next, let's add two grounds. Add the first ground over here and add the second ground over here and do the right click. And then let's connect these power voltages. Click here, 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 then click here, 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 and here. Okay, now we have provided power to our op-amp. Let's select the power values, do the right click, then do the right click over here, specify 15 over here. That is, we are specifying 15 volts. And over here, do the right click and specify minus 15 volts. Okay, now we have provided power to our op-amp. Next, let's add our input. Click here and place the input over here. Let me just do it actually somewhere closer. For example, over here we can place the input. Good. And then, or maybe a little bit down over here. Good. Okay, and let's add the ground. Here's our ground. Do the right click and let's proceed further. Next, let's add the two resistors and the capacitor. Click here, then do a right click, or actually do Control R, and add the first resistor. Place it here. The second resistor place over here, and do the right click. Then let's add the capacitor. Click on the capacitor, do Control R to rotate the capacitor, and let's place the capacitor over here. Good. And then let's change the names. If we go back to our graph, this resistor should be R1, this resistor should be R2, and capacitor should be C. So let's change these names in order to be consistent. So this is R1, this is R2, and then let's do the right click and let's call this resistor as C. Then let's connect everything. So click here, and connect this to the inverting input. Do the right click, then let's create the feedback. Go from here, click here, click here, click here, and here. And then let's do the same thing for the capacitor, connect it to the feedback loop, and here it is. Perfect. Now we have our capacitor, R1 and R2 resistors, and we just need to ground the non-inverting input. To do that, click on the ground, click over here, do the right click, and then let's connect this part to the ground like this, and that's it. Now we have grounded the non-inverting input, we have provided the input voltage, and we have our two resistors. The next step is to select the values. That is, we need to select the values of two resistors and this capacitor over here. Let's select the value of R1. So right click on R here and let's specify 10,000. That is, I'm specifying 10,000 ohms. Here for R2, I will also select the same value. Right click and select 10,000. Now I will have a gain of 1. And here for the capacitor, do the right click and let's select 10 to the minus 6. To do that, simply type 1U, and if you do that, you will see this abbreviation mu. This means that this is 1 microfarad, or 10 to the minus 6 farads. Okay, now we have R1, we have R2, and let's look into our amplification. We can see that the amplification will be 1 over here, since R1 and R2 are the same. Next, we can also calculate the break frequency, and I will do it later on in Python. However, before we do that, we need to select the value of our voltage. So do the right click on the voltage source and click on Advanced, and over here select Sine Signal. And over here we need to do several things. First of all, we need to select the amplitude. Here for simplicity I will select 1, and let's select the frequency. we need to select the frequency to be equal to the break frequency or the cutoff frequency in order to validate this simulation. So let's calculate this break frequency. Over here, I created a simple Python script that performs the calculations. Namely, here is my R2, here is my C, and over here I'm calculating the break frequency using the formula explained at the beginning of this tutorial, and let's evaluate this and let's see what do we have. And if I type Fn here, I will get my break frequency, which will be 15.923. So let's now copy this. Let's go back here and let's paste this value. That is enter 5.923. Namely, I expect that the attenuation of the output signal compared to the input signal will be 0.707 since my input signal is actually at the break frequency. And let's click OK. And now you have a sine signal here. The next step is to call or to name the input and output points. So click on net and specify here y and click here. This is our output net. Then click here again and specify u and click OK and put u over here. This is our input. Now we have the output and we have the input. We have the sine wave. We have R1, R2. We have here the capacitor, and that's it. We have provided power. We have grounded everything, and let's simulate. To simulate, click here and let's specify the stop time to be 1 second and click on OK, and then let's click here. We are doing transient analysis for 1 second, and let's click on play button and nothing is shown over here. That's perfectly normal since we need to explicitly select what we want to plot. Do the right click here and click on add traces and click on V of y. That is, we want to plot the output signal or the voltage at this output node, and click on OK. And here it is. Here is our output voltage. For comparison, let's plot the input voltage. Do the right click, then click on add traces and click on V of u. And here it is. Now we have the input and we have the output. First of all, the input is a pure sine signal. Its amplitude is 1. Let's validate that attenuation of the output signal is 0.707. Click here on VOY and this cursor will appear. If the cursor doesn't appear, do the right click and you can place cursor on an active trace. So you can do this. And now if I move this cursor, let me clear first of our cursors, do the right click and let's clear our cursors. Then let's do click here and the cursor will appear. This is enough. So let's now do the following. Place the cursor at this maximum here. Okay. Place it approximately at the maximum. And let's see what do we see here. We see approximately 705, 706 millivolts. This is actually 0.706 or 0.707 volts. And we can see that the attenuation of this system is actually at this break frequency 0.707. This means that we have properly simulated this circuit. And that's it. Simple as that. In this way, you can easily simulate any low-pass filter. Okay, that's all for today. Thanks for watching and see you in the next video tutorial.